All right, so the second course, you're gonna notice it's quite different than the first one, in that this will be a lot more applied. The calculations that we'll cover in this, well, it's a very applied. Both courses are applied, but this one will has to do with mostly calculating monitor units and calculating dose within the patient, and how to measure dose within the patient, and coming up with dose formulas and dose functions. And some people have more trouble with the first part. Some people have more trouble with the second part. This second part here may take you a little while to catch on because it's completely new. It's kind of like new math, right? So once it clicks, everything will make sense. But at first, the best way to approach this is just to do a lot of practice problems, a lot of calculation problems. And so the functions and the calculations we'll do here are the calculations that you typically do in the clinic to calculate monitor units. So these are really important that you get a good grasp. And today, and then you might ask yourself, well, why do I need to do that? There's treatment planning computers and there's monitoring and calculation programs. You folks have seen the computers, and have you seen RadCalc or ImmuneCheck, those kinds of. So those software programs are out there, but we're users of the program, but we're not just button pushers. We need to know how the data gets into those programs. We need to know how to check those programs, to verify those programs, to make sure that they're correct. So we need to be able to do all the calculations those programs are doing on a manual basis. Of course, isodoses are hard to plot manually, but monitor unit calculations, basic ones are easier. So we'll work on that. First thing we're going to get into is electron density, and this is just a quick overview of electron density. And the reason we cover electron density is because today, when we do isodose calculations or monitor unit calculations, we need to consider the density of the number of electrons inside the patient. So we know that in air there's going to be less electrons per cc. In bone there's more electrons per cc. In metal there's more electrons per cc. Those are important because that's going to determine the attenuation of the beam and the isodose distribution. So we need to know something about electron density within our patients and what that means. So electron density is especially important for I'm pointing over here like there's a projector. Electron density is especially important for Compton interactions because at our energies, at our high energies, 6 MV to 20 MV or 18 MV, we're in that Compton region. And we know that all the processes take place at those energies, right? I mean, photoelectric takes place because photons scatter, and eventually the energy gets low enough where there can be photoelectric process. But the predominant process is Compton effect. And Compton effect is affected by electron density. And you can think of that as just density of material. How dense is this material? Because electron density and density of material are pretty close. I mean, they're pretty proportional to each other. Also, you can think of it as even just mass. Something that's heavier is going to attenuate more than something that's lighter, because of the density of this material. And then you can also say, well, the atomic number has to do with that too. But in effect, what we're looking at is we're looking at electron density because the Compton effect depends on how many electrons per cc are in the material. So materials with different electron densities will attenuate photons differently. So we want to use plastic phantoms. Turn on this pen here. So we want to use plastic phantoms because plastics can be made with different recipes. You can mix different materials in plastics and make them in different shapes. So we use plastic phantoms to simulate, for our test, to simulate patients, and that's what a phantom is. So let's look at what electron density is. Electron density can be electrons per cc, and so the electrons per cc of a material is equal to the mass density of the material. That's the one we recognize. And then times the Avogadro's number, so that's 6.02 times 10 to the 23. It's a big number. Times the atomic number divided by the atomic mass. So if we look to see if the units work out, so this is mass density. The mass density is kilograms per cc times Avogadro's number is in units of what? We can say atoms per mole. Okay, atoms per mole. Okay, there's 6.02 times 10 to the 23 atoms in 1 mole times Z. Well, Z can be Z is the atomic number, but it's also the number of electrons per atom, right? So in a stable material. So this is electrons per atom. Okay, that's Z, divided by A. And A is kilograms or grams per mole. Right? So it's grams per mole. And then just to make these work out, let's make this this can be grams per cc. Okay, so make that grams per cc so the units work out. So if we cancel grams here out of grams there, mole comes up to the top and cancels with this one, and then we got cc here, and this atom cancels with this atom, moles cancel, grams cancel, and so we're left with electrons per cc. Okay, and that's what electron density is. All right. So, and then what's Z over A? What's Z over A is for a substance that's not a pure element. Then what you have to do is you have to figure the sum over the individual elements that make up that element. Okay. So the electrons per cc of a plastic, you need to look at all the elements within that plastic, and take the Z over A of the ith element times the weighting factor of how much of that element is in there, add them all up, and you get the Z over A, and then you can use that to put in here for a compound element for a compound material, solid water, for example. Okay, so that was just an aside on electron density. And okay, so dose functions now. Let me minimize this. We don't need to look at this all the time. All right, so having dose functions allows us to calculate the dose or dose rate to any depth for any field size after having been given a known dose at another depth and field size. So the relative functions. Basically, what a dose function does for you is if you know what this function is, and you have information about this function, and you know the dose at a particular depth for a field size, you can calculate the dose at another depth and another field size, okay, based on this function. Okay, so used for calculating monoid units. Dose functions can be tabulated as functions of field size and depths. What's an example of a dose function? Or have you seen tables of depths and field sizes? Have you seen them before?
Yeah. We did a calculation in IROC in the final exam.
What was that table used?
That was equating rectangular field sizes, square field sizes.
Oh, okay. Okay.
There was no one. Was there one for PDD?
So yeah. PDD is a dose function. We'll talk about that.
And the TMR maybe.
So, for example, if we know the dose of Dmax for 10 by 10, in the previous part of this course, I kept saying that's the reference condition, right? Dose of Dmax for 10 by 10 field at SAD is 1 centigrade per ml. That's the known dose. So, everybody knows that. If you go to a clinic, it's either SAD or it's SSD, okay? Where you have 1 centigrade per ml. So, once you know that, then if you have a dose function, then you can calculate what the dose is at 10 cm, for example. You don't have to measure it, the dose function. You're going to use a dose function to calculate that, okay, by looking at a table. So the first dose function we're going to talk about is PDD. And PDD, these brackets here, the arguments inside these brackets here, this is energy of the beam, so 6 MV, 10 MV, 18 MV. This is field size. Right? So what are the ranges of field sizes that we use in radiation therapy?
0.4 to 40.
0.4?
0.4 by 0.4 to 40 by 40.
Okay, 0.4 by 0.4 would be like a radiosurgery beam, like a stereotactic radiosurgery. In regular radiotherapy beams, usually 4 by 4 is the smallest field that we have PDDs for, and then that goes up to 40 by 40. And then depths. So PDDs depend on depth. What do you think the depth range is? Range of depths. Usually we have PDDs down to a depth of 35 centimeters, from 0 to 35. Okay. We don't need to go much more because typical separations, patient separations, don't go much beyond that. So if we were treating elephants, we'd probably have to scan our PDD a lot deeper than that. Otherwise, I mean, you could have a PDD that stops at 35, and you may be able to extrapolate that out linearly, or with a polynomial. But but for humans, scanning down to 35 is sufficient. And then SSD. So PDD also depends on SSD. What's a typical SSD?
80 to 130.
Yeah, a typical SSD is 100.
Yeah. So,
Yeah, the most common SSD, but you can have 80 for cobalt units. Some cobalt units are calibrated at 80. Okay, so you can have 80 SSD, and sometimes you'll treat patients with expanded SSDs. So PDD depends on energy, field size, surface depth. You guys will have to know how these affect PDD, each one individually. Okay, we're going to talk about that today. So PDD depends on energy, field size. Now the field size that we talk about, remember field size diverges, right? So the field size that we talk about when we refer to PDD is always the field size at the surface, and depth and SSD. SSD is constant for a particular PDD table. So if I give you guys a table of PDDs, that will be a table for a particular SSD. If I want you to work on a different SSD, I have to give you a different table. Why? Because PDD is SSD dependent. So PDD is equal to, so here's the formula for PDD. Dose at depth, at any depth, divided by dose at Dmax times 100 for a set field size. Okay, defined on the surface. So that's what PDD is. So if I tell you guys, go measure PDD in the clinic, you would set up a solid water phantom or a water phantom, and you take a measurement at a depth, and then you take a measurement at Dmax, and you divide the two for a certain field size, and you say the PDD for a 10 by 10, depth of 10 is 0.9 or whatever it is. Okay, it's very simple. That's all it is. Of course, we need it more than one depth, so things get complicated because we need a lot more numbers in there. All right, so this is an example of a water tank. You can see the water in there, and then there's a chamber at a depth D, and then we put a chamber, and then we could place our chamber at Dmax as well. We take the measurement of this divided by the measurement of this, and our PDD is going to be higher or lower than 1?
Which one?
PDD. Is PDD going to be typically higher or higher or lower than 100?
Lower.
Huh? Lower, typically less than 100, typically, right? Because the dose down here is going to be less than the dose up here, because it's, number one, it's further from the beam, and number two, it's deeper and there's more attenuation. Okay, so these PDDs are going to be pretty much smaller than 1. Okay. So measuring PDDs. So to measure a PDD, keep the SSD constant. We usually measure it in a scanning water tank. It's a lot easier than stacking a bunch of plastics and changing the depth and changing the thickness of the plastic. PDD increases with field size. Okay, so remember that. And it increases with SSD, and it increases with energy. So those three factors will increase PDD, and we'll explain how they do that. Dmax decreases with field size. Dmax, so the depth of Dmax gets shallower, it decreases, it gets shallower as I increase my field size. Due to higher contribution of low energy electrons with larger fields. Larger fields allow more of the collimator faces to scatter low energy electrons. So if I put a chamber at Dmax, now we're not even measuring PDD now, we're just measuring the reading we get from our chamber at Dmax. So I have a chamber at Dmax, and I shoot at 5 by 5, take a reading, 10 by 10, take a reading. Sorry, we're talking about the depth of Dmax. If I scan a PDD around Dmax for the different field sizes, what you're going to see is for the small field sizes, so there's one PDD, will look like that. And then as my field size gets larger, it's going to look like, start looking like this. So Dmax is here for the small field size, and then becomes shallower for the larger field sizes, because there's more scatter. As I open up my field size, there's more scatter off the job faces. I'm creating more area for the photons to scatter. And so if I'm creating more scatter, I'm creating a higher component of low energy photons. If I'm doing that, those low energy photons are going to deposit more of their dose superficially. They're not going to penetrate as much. Okay, so that's why a larger field size makes Dmax shallower. If there's not enough water at the bottom of the tank, deeper depths will not be accurate due to lack of backscatter. So this is something else to think about. If the tank, okay, so here's the tank, and here's the field, and say you're scanning a chamber from here all the way down to the bottom. Well, up here is fine. There's full scatter. In other words, as photons scatter, they're scattering forward towards the chamber, and some of them are scattering backwards towards the chamber, and that's fine. So as you get deeper, that full kind of isotropic scattering condition exists until you get here. When you get down here, the scatter that occurs here that scatters into the chamber, and sideways that scatters into the chamber, but we are now missing all the scatter that comes from backscatter. Okay, so that's gone. So when you're measuring PDDs, it's important not to scan all the way down to the bottom of the tank, because you're going to miss that scatter. Okay. And if the patient is large enough, I mean, if they're larger than 35, there will be scatter inside the patient, which you're missing from the tank. So PDDs always assume full scatter, and that's in a patient that's not 100% accurate, because the dose in the back of the patient, there's not full scatter in the back of the patient. Okay, but we have to make an assumption at some point. We have to see either full scatter or not full scatter. So we always scan with full scatter. So well, let's think about the implication of that. So if we scan with full scatter, and now we have a patient here, and we measure, and the treatment planning, here's our beam, and the treatment planning computer gives us some isodose distribution that looks like that. There's some inaccuracy down behind the patient, right? Would you think that the planning computer would calculate a overdose there, more dose than is actually there, or less dose than is actually there?
It would calculate more dose.
Correct.
You're not receiving the backscatter.
Yeah, it would calculate more dose than is there because you've measured your PDD for full scatter conditions where there's more dose. True. Okay, measuring PDD continued. Let's see. There. Okay, get a little animation going here. So this is how we measure PDD. Place the chamber at some depth. And we move it upwards, and as we're moving it upwards, the chamber is connected to an electrometer. The electrometer is connected to the computer, and this is the computer screen. And you folks have seen that, right? When we work together. Okay. So size the final surface. All right. And then the reason we scan from the bottom up is if we start at the top and we went down, the meniscus, there's a meniscus that will get pulled. The chamber will pull a meniscus as it goes down, and there's a little bit of a wave that gets formed. So, and that doesn't happen when you go from the bottom to the top. So as this chamber goes, if we start from the top, it pulls the water tension down, and as it breaks the tension, it creates a little wave. And that'll show up here as incorrect data at the surface. So we always scan from the bottom to the top of the bottom. All right, PDD dependencies. So higher energy, we said that PDD depends on energy. Higher energy will have deeper Dmax and will be more penetrating. So this curve here, the curve could be for 6 MV, for example, and then this is just hand-drawn curves, and this may be for a 10 MV curve. Okay, so if you see, you'll get used to seeing these curves and these traces of PDDs, and you'll be able to recognize a 6 MV from a 10 MV. The 10 MV is, you'll see the Dmax. The first thing you can look at is where's Dmax. So for 6 MV, you folks remember what Dmax is? That's kind of the first fingerprint of a PDD. What's the Dmax for 6?
2.5, yeah.
That's the Dmax for a different energy. What energy is that? That's 10x. 2.5, 2.4 is 10x. 6x is going to be less than that. So 10x is 2.5. 6x, how about 1.5? Okay. So that's the first, if you look at a PDD curve or a PDD table, that's the first thing you look at. And by the way, these numbers are typically given for a 10 by 10 field. Okay. So that's how you'll be able to recognize. Okay, so the larger field size appears more penetrating at deeper depths, but brings Dmax closer to the surface. Okay, so the first effect, energy. Second effect, large field size. So as the field size increases for the same energy, now we're talking about 6x, 6x, but two different field sizes, like a 5 by 5 and a 30 by 30, they'll also look different. I wonder if I have a picture of that. they'll also look different, and they'll look something like that. The large field size will look like that, and the small field size will look like this, so large and small. But the difference between a large field size and a small field size, besides the penetrating ability, is the Dmax is shallower for a large field size, which I just explained, right? So that's how you can, if you see two curves overlaid on each other, and one is more penetrating than the other, you may say one looks like it's higher energy, but it might just be a larger field size. Okay, so be careful about that distinction. And the way you can tell the difference is that the large field size will have a shallower Dmax than the small field size. But if they're two different energies, the high energy will have a deeper Dmax than the lower energy. Okay. Oh, why does a larger field size look more penetrating than a smaller field size?
You have higher fluids.
No, fluids could be the same. The central axis of fluids could be the same.
Okay.
But the fluence is larger at the periphery, off to the sides, because the field size is bigger. Okay, so if you're now creating more scatter by opening up the field size, so you're making more photons available to be measured. All right, so here's a small field size, and here's the chamber that's measuring. Here's the surface, and it's measuring. You measure a PDD. And now you increase the field size. And as you do this, you're now creating all this extra volume here that's available to scatter into the chamber. So that wasn't there before. Okay. So that's why it looks more penetrating. It's just more dose because of this extra scatter. Okay, greater SSD increases PDD. So now the third parameter that affects PDD is the SSD. Why does a greater SSD increase PDD? Do I have an example? Let's see. I just asked this. So why does a greater SSD increase PDD? Let's think about that. So again, you could think of this being SSD 120. This could be SSD 100, for example. And don't worry about the Dmax for now. Why does this look more penetrating? What do you think? As you get further away, greater SSD. Any guesses? Well, let's think of it this way. What makes this intensity drop? Why does it go down, not up, and not straight?
Because of the simulation.
Simulation, but there's one more effect.
Inverse square.
Inverse square. You're getting away from the beam. You're traveling away from the beam. When you're measuring PDD, you're going from here, say we start up here this time, and we go down, you're getting attenuation due to the thickness, and you're also getting further away from the source. Okay? So there's two effects. Okay, now. So now let's take an exaggeration. Here's the source of radiation, and there's 2 points, here and here. And we're going to measure the dose here, and we're going to measure the dose there. Obviously, this one's going to be less because, and this is an amp. Obviously, this is going to be, the ratio between these 2 points is going to be less than 1. If I take the dose here divided by the dose there, it's going to be less than 1. Now, let's say this distance is 10 cm here, 10 cm to this point, and maybe 11 cm to this point. And we can calculate the inverse square factor there, right, between the two. Okay, now let's take these points, they're 1 centimeter apart, and let's put them a mile away. They're still 1 centimeter apart, but now they're a mile away, 1 mile, okay, from here to here. Is the ratio between these points the same as the ratio between these points, the dose ratio? Okay, if you figure out the inverse square factor between those two, these are going to be pretty much the same, because the inverse square factor increases as you get closer for a certain distance apart. It increases as you get closer. All right, so now let's take that back to this water tank. So we have a water tank at 100 SSD, and then we measure PDD, and then we move that surface down to 120. So every point here, every combination of points, as you go to 120, the ratio between them will be smaller. The difference in dose between those 2 points will be smaller because those 2 points will be further away from the beam. Okay? So the difference in dose between this point and Dmax will be, the ratio will be smaller. The inverse square ratio, not the attenuation. Attenuation is not affected here. It's just the inverse square component. It'll be smaller. Okay, so then there's the decrease in intensity between those 2 points is smaller as you get further away. Okay, so the inverse square, and if I move this tank a mile away, then the PDD will only be basically affected by attenuation, and it won't be affected by inverse square anymore if you get far enough away. Okay, and in effect, you do see a small difference between 100 and 120. You do see it. It's measurable. Does all that make sense? Okay, so why does larger field size increase PDD? Let's just go review.
Scatter.
Okay, scatter. Why does greater SSD increase PDD? We just talked about Inverse square. A decreasing, if you would have to explain it to somebody, you could say a decreasing inverse square effect as you get further away, as you increase SSD. And then why does larger field size decrease Dmax?
More low energy electrons.
Yeah.
Collimator scatter.
Or photons, both, yeah. Okay, and, oh, what's all that?
All your drawings pop back up.
Oh, the drawings pop back up. Oh, so every time I hit next slide, did they get deleted?
I think it's
They
because
were
there's
just on the
animation.
previous slide.
Oh, yeah, okay.
Yeah.
All right, well, that doesn't matter too much. Go to page 120. Who's got time? So let's go to page 120 and look at the 10 PDDs, just to get an idea. Oh, page 120 might be the red book.
It says 820.
Yeah.
820, sorry. Oh, then that's appendix.
MVX rated PDDs.
Okay. So that's A11 here.
Oh, A11. Well, table A11 1, page 820.
Oh, it is page 820? Yeah, that's page 820.
A18.
It's A18 for yours? Okay. Okay, so let's just take a quick look at these. And then when we talk about PDD functions, you won't see a function that you used to see like y equals x cubed minus. It's not a function of unknowns. You'll typically see tables. Okay. Because these are a lot more easily, it's easily more accessible if you go to the table and you're just usually looking for a field size and a depth and you can quickly go to that number. So look at the 10 by 10. So 10 by 10, as you go, 0 is 12.5, the PDD is 12.5, and as you go towards Dmax, 10 of V Dmax is 2.5 in this case. You see how it increases? That's the build-up effect, and then it decreases down. So some things, you should memorize some important numbers for PDDs, and that is the PV for a depth of 10, okay, for all energy. So you need to memorize Dmax's, and you need to have a good idea of what PDD for a depth of 10 is. And so PDD for depth of 10, for 10 of V is 73. Is there 6? I don't think they have 6 of V here. There are 4. That's odd, they don't have a 6. They have a 4, but not a 6. It's so rare to see 4 in V1X. Okay? And so as you go across, so as we go down, we know it's going to decrease. And for the larger field sizes, the rate of decrease is slower than for the smaller field sizes. So let's go across. So let's do a depth of 10 and move from left to right. So 0 by 0, that's a theoretical field size, obviously. Going across, we have 67, 70, 71, 72, 73, 73, 74, 74.7, 75.3. And so it increases as you move across as well. And so that makes sense, right? Because we said the PDD increases for larger field sizes. Okay, and then move across, move down. Okay. And then look at the top field size at the top. They're all square field sizes, aren't they? Do we treat our patients all with square field sizes? No. So we have to convert it, right, from rectangular to square, and we'll talk about that. Okay, there's another dose function called a Mayneord factor. You guys just need to know what this is. We don't use it too often. I think we used it a lot more in the past when PDDs were used more commonly. PDD tables were used more commonly for hand calculations. So remember how I said the PDD table is for a particular SSD. And so back in the day when they wanted to treat different SSDs, they didn't want to have tables and tables of all the SSD. So there's this conversion factor called the Mayneord factor, and that converts your 100 SSD PDD table to an X SSD, 110 SSD, 105, whatever you want. And it doesn't convert the whole table. It usually converts the PDD that you need. So it works like this. So this is the inverse square factor that you guys know about. So dose 2 is equal to dose 1 times ISF. We've already talked about that. Now the Mayneord factor converts a PDD function from an SSD to the other. So the PDD for SSD2 is equal to the Mayneord factor times the PDD of SSD1. So the assumption is that you've got one PDD for a particular table of SSD1, and then you're going to calculate this to convert it to an SSD2. And this is what the F is. Okay. So say SSD2 is 110. You put in 110 plus the Dmax of your beam. The SSD that you have, say, is 100. So you put in 100 here plus the Dmax of your beam. Again, 100 here, 110, and then these are the depths that you're treating at. And that's the depth that you're treating at. And then both are to the power of 2. So that's the Mayneord factor. And there's a derivation of that in Kant. I think they derived that. It's a very simple derivation. Okay, SSD versus SAD versus SSD setups. So on SSD, the field size is defined on the patient surface. Every gantry angle, as you rotate the gantry around, I should just turn this. Hold on, give me 5 minutes. This is almost. This is Alex. Yeah, hi. Yeah, I'm teaching on in the middle of the class.
You guys excited for the treatment planning course?
I heard it's a tough one.
I'm excited. I saw the Dr. Tom put in all the sources and gave them all values and just started changing numbers willy-nilly. And I'm like, what are you doing? And then the doctor came in and 10 minutes, probably went through about 60 slices and traced every organ. And I'm just like, what? You have a massive gray blob. That's one organ. That's a different organ. They look the same to me. How can you do this? I can identify the spinal cord. And I think that's the stomach.
We're gonna get a ton of practice with a ton of homework, is from what I hear.
Yeah. Well, other than the fact that I plan on going for like 3 days, I shouldn't have a problem with homework.
I guess we'll see what Theo gives us for our first week's homework.
Yeah.
And he still wants us to do that project, the spreadsheet.
Yeah. I still want to talk to him and see if we can get remote access to it, because if I could work on that during downtime at clinic, that would be awesome. Granted, I didn't have any downtime until like 5:30, but
I mean, the computers are here, so Dr. Markovic probably knows if we have remote access to them or not.
that's true. Do you know what programs we have here for dosimetry?
No, Theo mentioned them in the email though. It's like, was it XIO or something?
Well, we may have an Axio, because I think it's Axio. I'm not sure if we have more than one treatment program.
It's whatever we got for free.
Yeah, I know Lutheran General donated a system, and I think that one had Axio on it. But Brian and Harold were talking about it over my head, and I'm just kind of sitting there twiddling my thumbs going, I kind of understand what's going on.
Whatever we have, I assume it's at least somewhat common.
Yeah. Axio is one of the main ones. It's just I see him going through this huge venue, and I don't think they use that. I know they use Mosaic, but what's Axio?
I don't think we have Mosaic.
Find out when we go to class and he pulls up the treatment plan, it looks familiar, and it's Axio. You go, hey, that's the one we can build it. I want to say that the ones they were using were not the same as the one that they donated to campus.
Maybe it's just different versions.
No, they were different names.
If anything, we'll find out at 5:30.
Yeah, 5:30.
And then when class starts,
I'm starting at 5.
Is it 5?
5 at 5.
Yeah, I thought it was 5:30. So.
Yeah. This is 9:30. Dr. Hans is 1:30.
Yeah,
That
yeah.
starts at 5. Busy day.
Where's Dr. Han's class?
The conference room.
Is it?
Yeah.
Okay, I thought his was the different one. I thought Theo's class and this class were supposed to be in the conference room.
If it changed, I haven't gotten the memo. Which would be a first.
I guess it won't hurt to meet in the conference room. I'm sure everybody would be there or around.
What is our upperclassman's name?
There's 2 of them.
Okay, what are our upperclassmen's
That's a
names?
good question. They're tagged in the emails every so often. You can just load up an immediate email and they're probably on.
Because I think one of them is Stephanie, but I'm not sure on that. Just pull up an email. But I need to check. I'm not enrolled in this on D12, so.
What's the deal with our radiation safety class? Like, is there a time limit to finish that?
Yeah, 17th.
To Thursday, I think.
This Thursday?
Yeah.
Oh man, there's like 8 classes in the.
Yeah, I'm going to be working on it between classes.
I guess I'm going to start now. I thought I'd have like a couple weeks.
No, that's why she was like urgent,
Yeah,
sign up for it right now.
I read like the syllabus for it. I don't think it mentioned it was due, but
She said in another email.
Yeah.
Gmail.
Did you say he wants to add one more class?
he didn't say anything.
We
recently.
haven't officially scheduled the second course,
Oh, yeah.
but I know he wanted to have a course here and a course on site.
Yeah. Then we can do something
Sorry, guys.
practice on the
Have a-
training system.
He hasn't like brought it up again.
We have an inspection at the hospital by the JCHO, Joint Commission, and what the JCHO is involved with, they accredit whole hospitals. So they put their stamp of approval on a hospital. So, and they come around once a year, and it's a big deal whenever they come around. So anyway, they ask the question on physics. They usually don't go to physics, but they go to physics, and they ask them a question, and they said, all right, here's the chart. There's no physician signature on this treatment plan. How do you guys know that this has been approved? How does everybody know? And and they said, well, the therapist said, well, that's a physics question. That's how it got to physics. And so they went to physics, and the JCO said, how do you know it's approved? And they said, well, if it's printed, it's been approved. And JCO said, well, there should be a signature on here, by the physician's approval or some kind of stamp or something. And they said, no, our policy is if it's been printed, it means that it's approved. So they weren't too crazy about that. They wanted to see a written procedure somewhere that says, that states that, because this is just thing that we could be making up on the fly, which is our policy, but we have, and then they said, how does the physicist know that the plan's been approved? Is there a signature or is there something? And so we know because the physician tells us. We sit next to the physician, they look at the screen, they say the plan's approved, and that's how we know. Well, I don't know if Jacob's going to buy all this. I think they want to have some kind of procedure where the physician sits down and types their little login password, and that's how it gets approved. Or signs a piece of paper, and that's how it's approved. It might not be enough for the physician to tell the physicist this plan is approved. So they call me because they want to see if we have something in writing, because I wrote up all the procedures, and we really don't. And, it's mostly verbal, and maybe yesterday's age that was okay, but today that might not be okay. Today we have to put everything in writing. So, all right, let's keep going. SAD. So back to SSD. So if you're going to treat, hello, yeah. Yeah. Oh, maybe you should. Yeah, you probably don't want to bring that up. Yeah. Okay. Okay. All right. See ya. Bye bye. Okay. As the gantry is rotating around the patient in an SSD setup, the field size changes, right? Because if the gantry is pointing in the AP and then rotates around with the isocenter in the middle of the patient, now this SSD is going to be less than this SSD, because this is wider in this direction, at least for me. Okay. So as that SSD changes, you'd have to go to a different table for each field. So that's not practical. Okay. So there are three per gantry angles in an SSD setup. There's three variables. One is field size, two is SSD, and three is depth. Okay, so those three things are three possibilities that may change. In an SSD setup, the field size may change with gantry angle, depending on the tube direction and size. SAD is constant. So with SAD setup, if you put the isocenter at the center of the tumor and you rotate the gantry around, there's two variables. There's depth, and there could be field size changes, because if your tumor in the AP, say the tumor looks like this. So in the AP direction, the field size would be this big, but then in the lateral direction, the field size would be this big. You see how that gets narrow for the lateral direction. So there could be, so the difference between the AP is depth, and for the lateral, the depth is different and the field size is different. So that's two variables. So it's simple. An SAD setup simplifies things rather than setting an SSD at the surface all the time. And also, if you're going to keep the SSD constant for an SSD setup and treat patients for like 100 SSD for all fields, you need to move the patient. You're going to have to move the patient. You don't want to do that. Okay. So SAD setups became a lot more common after a while. SSD setups were common originally because the original linear accelerators were not rotational. They were, and actually I trained on one, and it was the gantry was up there, and all it did was the head went up and down. That's all it did, and the patient was placed on the treatment table, So they could change the SSD by moving the head up and down, but if they wanted to treat from a different direction, they had to turn the patient on their side or then turn them on the back. So that originally, that's how Linux worked. Eventually it became rotational, and once it became rotational, everyone figured out that an SAD setup is more convenient. So let's move on to more dose functions. So TAR and backscatter factor. These are functions that you need to know about. People don't use them that often these days, but you need to know about them. So TAR function brought about for rotational therapies. TAR function is an SAD function. PDs became too cumbersome because of the reasons I just described, due to SSD differences between gantry angles. So TAR is equal to the dose in tissue at a particular depth divided by the dose in air. Okay, so that's different. So now we're taking the dose at depth divided by the dose in air. What was PDD again? Remember what the function definition for PDD was?
Dose at depth divided by dose at Dmax.
For a certain field size on the surface.
Yeah.
Okay. Now, dose at depth divided by dose at air. For the same distance from the source. So that's different than PDD, because in PDD, the dose at depth is a different distance than the dose at Dmax. Okay. This is the same distance. And I'll draw the triangles in a second. BSF means backscatter factor. It's a special case of TAR, where depth equals Dmax. Okay, now TAR depends on depth and it depends on field size. Backscatter factor doesn't depend on depth because depth is constant, Dmax. Okay, field size, treatment depth, and SAD is constant. Okay. TAR is practically independent of distance to source. Okay, so what does that mean? So if the SAD, so TAR comes in, you might find tables of TAR. And say the SAD is 100, and then if you find another table where the SAD is 80, you can use the same tables. Okay, the SAD 100 and the SAD 80 are going to be very close to each other. Not identical, but they're going to be very close to each other. Okay, so TAR is not dependent on distance to source. All right, so here are the triangles. So TAR equals, here's the function for TAR, equals the dose in tissue, or dose in medium, dose in some material. And TAR depends on, as I said, depth. It depends on SAD. And it depends on field size. Now, a minute ago I said it doesn't really depend on SAD, but there's a slight dependence, not too much. And it depends on field size. So these are the two big ones, depth and field size. So divided by the dose in air. Now, dose in air, we could forget D, right? There's no depth in air. So D's gone. For the same SAD, so this distance and this distance have to be the same when you're calculating TAR. And it also depends on field size in air. Okay, so TAR equals, you take a chamber, take a reading here, and then same chamber, get rid of the phantom, keep the same distance from chamber to source, and then take a reading in air. That's TAR. Why do you think TAR measures dose in air? Why do you think we need this air measurement? It goes back to the days when people were taking measurements in air. Okay? People back a long time ago were doing measurements in air, and they would put chambers in air in the days of Cobalt-60 when there weren't too many linear accelerators around. And everything was referenced to a certain dose range in air for a Cobalt-60 beam. Okay? So if you take a measurement in air for Cobalt-60, you need to measure the dose in the patient at some point. You need to know what the dose in the patient is, so you need a function that relates your measurement that you've taken in air to the dose in the patient. That's what TAR is for. So measuring TARs, how do you measure them? Set up a water tank with a chamber underwater at the machine isocenter. Take a reading with the chamber, then change the water level, so you're changing the depth. You're not moving the chamber. Take another reading, and then this is constant, remember. Repeat. This is not constant for PDD, right? This changes for PDD. So for TAR, it's constant. Repeat A and B for all depths, okay? And then repeat A and B for all field sizes, and that builds your entire TAR table. Then measure the dose in air at the machine isocenter for several field sizes, as you did here. Then divide all the readings that you took in water by all the readings you took in air. Remember, TAR is dose in medium divided by dose in air. Okay? So all the water measurements divided by all the air measurements. Yeah, and then, so for these measurements where the depth changes, you're going to be dividing by the same value in air because there's no D in air. So you're just going to be dividing by that field size, whatever field size you measured. Okay. So it's easy to do in Excel. Okay, narrow beam TAR. So this is a special case of TAR. For an imaginary beam of field size 0 by 0, so now we're looking at only primary photons, photons that are going straight, no scatter. The TAR can be expressed by the exponential attenuation coefficient. Okay, so here's the first time we can express a dose function by a simple equation. Okay. All the other dose functions, PDD and the other TARs, those are all measurement-based dose functions. We have to measure them. Okay. We can't derive them from any. There's no way of deriving them from some basic principles. So we have to measure them, or we can use Monte Carlo calculations to calculate them. Okay, so most of us prefer to measure them. So the TAR for a 0 field size at a depth of D, there's the variable, is equal to a simple exponential, e to the minus mu of t minus d max. So that's your exponential attenuation equation. That's all that is. So for primary photons, when there's no scatter, you can use exponential attenuation. Okay. Okay. So mu for cobalt 60 is that. The relationship between PDD and TAR. So this is we can calculate PDD if we know TAR and vice versa. If we measure PDD, we can calculate TAR. Okay, without having to take extra measurements. So PDD is defined as TAR at a certain depth and field size. And this is important here. The PDD is defined at a field size field size 0. Field size 0 is at the surface for a particular SSD. TAR is defined at a depth for the field size at a depth D. Okay, those field sizes are different. Okay, so for a certain collimator setting, you're going to have a field size on the surface, but you're going to have another field size at a depth D, and you need to take those two into account. The backscatter factor is defined for the field size 0, and then SSD plus D max, SSD plus D all squared. So that converts from one to the other. And let's see. Let's see how we derive that. I took a couple of screen caps, so I have them on my phone somewhere. It's a picture of my cat. There it is. Okay. Okay, so all right, so what they do is they say D at depth, the dose at depth D for a point Q is equal to TAR, and this, I believe this is in Con. Yeah, I got this from Con. TAR for depth D and R. Now they say RD. RD. This means this is the same thing as my field size at depth D. I mean, they use R. Why do they use R? Because it's radius. It's just they want to use the word radius for a circular field. It's kind of an ancient way of describing it. Okay, times D in free space. Fs means free space, not field size in this case. That same point Q. Okay, and the point Q is at a certain distance from the source. And here they're drawing, looks something like this. The drawing is pretty similar to my drawing. Anyway, so D at D max. So the dose at D max for point P. This is a different point. Equals the dose in free space at point P times the backscatter factor. Now these come from the definitions. Remember, TAR is dose at depth divided by dose at free space. So we're just rearranging them. And the same thing here. Okay, this is just P is a different point in space. Okay, here I should probably draw it. Okay, so P is the point that represents P is the point that represents the distance to D max, and Q is the point that represents some point at some depth. Okay. Right. So then the PDD at a depth for a certain field size, and this field size, by the way, is at surface times F, and then their F is SSD really. So this is SSD is equal to the dose at depth D. Depth D for point Q divided by the dose at D max for point P. So that's just the definition of PDD. Okay, so it's the dose at point in tissue. It's the dose at point Q divided by the dose at point P. The dose at point P is D max. Okay, so that's just the definition of PDD. And then so PDD. So now what we're going to do is we're going to replace these two values into this equation, and that becomes so PDD TAR. Okay, so we're using that up there. Depth of D for R of D, and there's a difference between R and R of D. This is R at the surface. Okay. Times 1 over backscatter factor of R, that's at the surface, times D free space over for point Q divided by D free space for point P times 100, because it's percentage. They started with percentage, and I guess they thought it was a good idea because percentage is intuitive. But then after the PDD, all the other dose functions that followed were always ratios, because why carry this 100? You've got to carry this 100 everywhere, and then you've got to get rid of it when you're using it to calculate monounits. So they stopped using 100, but PDD because of tradition is still a percentage. Okay, so that's just how we derive the conversion between TAR and PDD. Okay, equivalent squares and circles. So we know that those tables are only in squares. How many slides do I have? 28? I think it's around 28. Anyway, it's equivalent squares and circles. Maybe we should take a break here. 10:30. Are you guys okay? Yeah, I should keep going.
I'm okay.
You okay? All right, are you still with me? I don't know. All right, I'm okay too. So equivalent squares, we know we need to go from a rectangle, which we treat our patients with, to a square, because that's what our data and tables give us. So column table 9.2 contains measured equivalent square data. What does this mean by measured? This means that at some point, somebody set up a rectangular field on the linear accelerator, put the chamber in the middle of the field, and they measure the dose rate. And then they vary the length and width of that rectangle, and then they measured squares. And they made equivalences between the dose rate they get on those rectangles with the squares. So if the rectangle is 12 by 6, they found that they got the same dose rate for a field size that was 8 by 8. Okay? So they made those equivalences. They made those relationships between rectangles and squares, and that measured data is in table 9.2. That's measured data. Okay? So, but they also found that there's a very simple relationship that also works, that makes dose rates for rectangles equivalent to dose rates for squares, and that's the 4a over p equation. So you don't need to go, you can go to this table of equivalent squares, which is the most accurate way of calculating equivalent squares, but you can also use this approximation 4a over p, which most people remember 4a over, a by the way is area, and p is perimeter of the rectangle. Okay. So, but most people remember it as 2ab over a plus b. And maybe I'll go to red. It's easier to see. 2ab over a plus b is equal to 4 times the area over the perimeter of a rectangle. If you do the math, it's equivalent. And so what's a and b? So a is the length and b is the width, or a can be the width and b the length. It doesn't matter. But 2 times A times B over the sum of the A plus B will give you the side of an equivalent square for that rectangle. So if you measure the dose rate for this rectangle in the center, and then set up this square, you'll get the same dose rate. And does that make sense intuitively? That it should be that way? I mean, this side here is narrower than the square, so you're going to get less scatter, but you're going to get more scatter from this length over here. Okay? What you'll also notice with rectangles is, as these edges start to get longer, we're going to keep this width the same, but as these edges get longer and longer, the dose rate will stop changing at some point. Okay, as they get longer, because the photons that scatter out here are just not going to make it to your chamber that decentralizes. So if you open the field size from, I'll give you an example, 35 length to 40 length, you probably won't measure a difference, okay, with your chamber, because that small extra area of scatter that you get out here and out here, well, that doesn't look like a square, but that's a square. That small extra area of scatter is not going to make it to your chamber. Okay, it's something to think about. Yet, if you use this equation and you put the numbers in, it will give you a difference. That's where you start losing the accuracy of using this equation. Okay, and that's where you should use tables. When your rectangles are long, then you should go to tables, and that gives you a more accurate equivalent square calculation. So buyer beware of this equation for long rectangles. The equivalent circle radius, again, you can take a rectangle and make it into an equivalent circle. All right, and that's just by doing this. Now you've got a square times the square root of pi, and that's the equivalent circle for this rectangle. So you can either go to a square or a circle from that rectangle based on this equation or this equation. Why would you want to go to a circle? We don't have tables that have circles, do we? All of our tables are squares. We actually do have tables with circles. I don't know if Khan has it, but I'm pretty sure Johnson Cunningham has tables with circles. And the reason we do that is because there's a machine called a superficial unit, and that's used, the treatment area is a circle. Okay? And so that's why you want to do that. If you have most superficial units, they're circular apertures, but say you want to treat a lesion that is rectangular, then you need to have that conversion. Okay, the tables will be circles, and you need to have that conversion to go to rectangles, or vice versa. You guys probably won't see a superficial unit. They're not that common anymore. Okay, let's do some examples. Dose at 80 centimeters from the source and air is 100 centigrade. Dose at 80 centimeters. I should say centigrade per minute. That's a little more accurate. Okay, from the source and air. What's the dose at 120? Okay, you guys have to do some work. Should I turn the lights on? What are we going to do? So it's 100 times, I'll start for you, ISF. Right? So that's equal to 100 times what are the numbers I need for ISF?
It's just the distances.
Right, just the distances.
So 80 over 120 quantity squared.
Okay. 80 over 120 squared, that's it. 8 twelfths, that's 4/3. It's 4. It's 4 over 6, 2 over 3, 0.667. So it's 0.667 squared, which is, I don't know, 0.5, 0.45. Okay, so 44 CGY per minute. Okay. cool. Now, sanity check always, there's two distances you got to use, you got to square them. Just make sure you put if you're calculating for the dose that's further, make sure you put the smaller number at the top. Okay. Next. Where's my slide changer? Oh, there's it. All right. So, use that 400 to down, 4. That's the answer. Okay, next example, dose at 100.5 centimeters in air for a field size of 5 by 5 for cobalt 60 is 100 centigrade. Let's just say per minute. Given the TAR of this, what is the dose in water at Dmax? Okay, so, should I draw the triangle? This always helps me. 100.5 from here to this point of interest. Oh, I should use these. What do you think? When I play with this marker, what do you guys think? Okay. So what's the dose in water? So we know what the dose in air is, what's the dose in water? So then here's the triangle, and we're in water, and then 100.5, we're at the same distance. Cobalt 60, Dmax of cobalt 60 is? It's 0.5, so we're at Dmax. Okay, so for cobalt 60. So that's Dmax. So what's the dose there? We know the dose here, it's 100 centigrade. We know what TAR is, what's the dose there? So always write down, when you guys are doing exams or assignments, write down the definitions of what these functions are. So TAR, that helps, equals dose in tissue divided by dose in air.
Free space. Yeah.
Huh?
Free space.
Yeah, free space. So dose in tissue divided by dose in air. Okay? So then if you want to know, what do we want to know? Dose in tissue, right? So just rearrange the equation. So dose in tissue equals TAR times dose in air or free space. Okay? So that's that. I'm not putting in all the dependencies in there because we know what they are and we don't need to put them in there. All right, so what's dose in tissue?
100 times 1.10.
Yeah, 101.9, right? Okay, so the dose is 101.9. Okay. Notice how I made this 100.5 so that it's very convenient. Okay, because we're in a Dmax. Let's do another example. So, how do we clear this? Clear, dry. Oh, nice. Okay. So use TAR or backscatter factor. We could use backscatter factor, right? Because backscatter factor is at Dmax, defined at Dmax. Okay, so dose in 100, TAR is dose in tissue over dose in air. Dose in tissue, blah, 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 blah. That's exactly what we did. Okay, fine. Example 3. The dose at 10 cm depth in water for a 10 by 10 field for cobalt 60 is 100. The SSD is 100. PDD is 57.8. TAR is 0.72. And then I give you another TAR for a different depth. For a different depth and a different field size for cobalt 60. What's the dose in air at 80 cm for the same field size? Okay, so let's write down what we know. I'm going to draw the triangle of what we know. Dose at 10 cm depth in water for a 10 by 10. So here, for a 10 by 10 field. Okay, 60. Cm depth in water for 10 by 10, 100 centimeters. No, SSD is 100. Okay, so this is 100. Okay, and this is 10 cm. And we know that this dose is 100. Okay, so how far is this point of interest from the source?
110.
110, right? Okay, so we know we have that. And this is what we want to know. We want to know what the dose in air is at 80 centimeters. That's what we want to know for the same field size. And so we're not changing the collimator setting. And so we have to do maybe we might have to do this in a couple of steps, right? Because there's two differences here. The distance from the point of interest, where we know the dose, is 110, and this is 80. And then the other difference is one is in water and one is in air. So we're going to have to do 2 steps. So what do you guys think we should? What's the first step we can take?
Convert it to dose and free air.
Okay, so we can. Okay, I'm going to erase this, so we know.
I think we got 3 steps.
3 steps, maybe.
Yeah, first we have to move the dose to the Dmax, then convert the dose of Dmax in water to air, and do our inverse square roll.
Do you guys think there's different ways of doing this problem?
Yeah.
There are. There's a couple of ways you could do this problem. All right, let's just do one way.
Do we have to move it to Dmax?
Because the TAR is 10 by 10, Dmax equal about 60. So, and the PDD is at depth at 10 cm.
Oh, the other tires for what?
Well, which way do you guys want to do it? There's lots of ways.
Yeah.
You just tell me what to do. All right. Where should I go? What should I do first? It's like a little puzzle, right? Yeah. How to get from here to there. What should I do first? Should I go to Dmax? Oh, well, there's only 2 things I can do. I can go to air, or I can go to Dmax.
Yeah.
I don't want to go deeper. That doesn't help me. Okay. So what do you think? Which one? Pick one.
Let's go to Dmax.
You go to Dmax? Okay. So how do we go to Dmax? So we're starting with what? We're starting with a known dose of 100. How do we go to Dmax? We've got to multiply this or divide this by something, right?
Yeah.
So how do we go from here to Dmax?
Multiplied by the inverse of TAR.
Okay, so let's remember writing the equations help. Equals dose at depth divided by dose at Dmax. And then TAR equals dose at depth divided by dose in air. Okay, so we got those. Which ones do we want to use first? We have, well, we can use this, right? Because we know this, and we want to know this. Okay, so dose at Dmax is equal to, flipping this around, dose at depth, which is this one, divided by PDD, right? Okay. So it's not times, it's divided by. 100 divided by PDD. Now let's make sure we're using the right PDD. So we want to use the PDD of what depth?
10.
Okay, so that's good. We have that. What about the field size?
10 by 10.
10 by 10. Okay, that's good. And then what's our SSD? 100. Okay, so good. So we have all that. So PDD 10, 10, 100. Okay, so that's going to give us our dose. And what is that number by the way?
Do we use it as a percentage, or do we use it as? Okay, do you use it?
We always have to throw the 100 under there. Okay, so what is that number then? What's 100 divided by? You guys ever see Khan Academy? You ever go on that website?
Yeah.
Khan Academy. I feel like Khan with the scribbling. All right. So what do I have? Who's got a calculator?
173.
So you did 100 divided by 0.578, right? And you got what?
173.
173 centigrade. Okay, so that's the dose at Dmax. Yeah, all we did was go from here to here. Great. What's next?
Now we go.
Here's what we're looking for.
To air.
Here's what we're looking for. So here's 80. Okay. So now we go to air, right?
Yeah.
Okay. How do we get to air?
TAR.
TAR. What do we do with 173? Divided by TAR, multiplied by TAR? Which TAR do we use?
We use the TAR field size 10 FD max. We take the dose divided by TAR.
Okay, so why is that? Because, well, here, let's look at the TAR equation. What do we have? What are our knowns on unknowns?
You know DD and TAR.
You know this, right? We don't know this, and we know TAR. Well, we have two TARs. Which TAR are we using?
10 D max.
Okay, so the 10 by 10 and D max, because we're at D max. Okay, 10 by 10, that's not 100% true, because it's 10 by 10 at the surface, and we're 0.5 cm away from the surface. So the field size is just a tiny bit bigger where we are right now, but it's negligible for cobalt 60 because D max is so small. Okay, so then 173, did you say we divide or multiply? Divided by TAR of D max. And what's TAR of D max? What's another name for TAR of D max?
The BSF.
BSF. Okay, so what is that? What do I get?
167.
167. 167. Does it make sense that we went from 173? Does it make sense that it dropped? Always, whenever you do a calculation, every step, say to yourself, does this make sense? Am I expecting a bigger number or a smaller number? Am I expecting a huge number or not so huge number? Do you expect a bigger number or a smaller number? You guys are thinking it's a little counterintuitive because, well, what about attenuation, right? Now, it's getting attenuated at Dmax and it's not an error. Why is it higher? It's higher because of the buildup effect. And actually, at Dmax, you'll have a higher reading than an error for the same distance, okay? So it's not something that you expect, but that's the case. Okay, so that in air, our dose drops a little bit, 167. Okay, so now, how far are we from the source? We're in air. How far are we from the source right now?
We're at 100.5.
Correct. So we're at 100.5 cm from the source. Cool. That's an S, by the way.
Okay.
All right, then we're almost there. How do we get to 80?
Inverse square.
Square. All right, so 100.5 times. What numbers am I putting in there?
Wait. Why is your 100? Isn't the 100.5 the distance?
Oh, yeah.
You have the. Yeah, thank you.
Just testing. Okay, 167. Okay. 167 times.
100.5 over 80 quantity squared.
Okay. What's that?
It's 264.
264. 264 centigrade. Okay, so does that make sense? We got closer, we got higher, right? Okay. Square. You just square it? Okay. All right, cool. So that's one example. Now let's do it a different way. So how many steps did we use, by the way? How many calculations? 1, 2, 4.
Oh, 3.
1, 2, 3, right? 3 steps. Okay. So now let's do it the other way. Losing fun. Yeah, let's clear. Let's clear these drawings. I think this is the answer. Divide. Yeah. So divide this by TAR. 260. Is that what we got? Yeah, we got that number. Okay. Now let's do it. Let's do it the other way. What's this next slide? Or determine the field size of 110. All right, let's do it another way. So again, we're starting depth of 10, and SSD is 100. Okay, what's the other way? And we want to get here. So the other way was go straight to air, right? Okay, so we're going to go from here to air, and air looks like this. There's no line. So if there's no line, it's in air. All right, so air goes like that, and now this is 110. Okay. So what do we use?
TAR.
Okay, so we have 100 as our starting point times or divided by, right? We say we're going to divide when we're going to air. So divided by TAR. Well, careful now. What TAR? Do we have this TAR?
We have the field size
We have
11
defined the field size if that's 10.
This 11, this one here.
Yeah.
But what about this 11? Are we okay with this 11?
I think it's wrong.
Well, what's the field size here?
You can calculate by the inverse square or it's not, yeah,
Inverse square?
inverse square.
No, they don't calculate field size by inverse square. Similar triangles.
Yeah.
Mm-hmm. So, similar triangles. We know the field size is 100 here, right? And we know this distance is 100. So if you have a distance and you have a side of the side of the triangle, you can proportion it out. So here's the SSD. Sorry, the field size is not 100, it's 10. 100 over 10 is equal to 110 over x. And that x is this. Okay? So x equals, right? Similar triangles. We use this a lot, by the way. Get used to using similar triangles and their relationships. Basically, with similar triangles, if you have, remember geometry back in the day, if you have two triangles that have the same, all these angles are the same. So angle, 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 that makes the triangle similar. But once they're similar, then you can apply these similarity rules. You could take this side divided by this distance is equal to this side divided by that distance, and give you all kinds of similarities. Okay, so that's 11. So then we need TAR 11 because that's where we are. That's where our point of interest is. TAR 11, and this is where things get confusing. Like what field size to use when you're using the TAR. Why aren't we using 10 now? Well, we're not using 10 because we're gonna try to use the TAR relationship, but the TAR relationship has to be for the depth and the field size of the point of interest. Okay? And before we used 10 because we went up to 10. We moved that point up to a field size of 10. That's why we use 10. Okay, so 10, and field size of 11, and a depth equals 10, which is equal to 0.72. So what's so this is 0.72. So then what's this? That's a small calculator.
It's 139.
Okay, 139. And then where are we now? So now we're in air at 110 centimeters away. We're still not there. Okay, so how do we get to 80? Yeah, inverse square. Do we need to worry about the field size for inverse square? You see, because this field size is going to be different than this field size, isn't it? Do we need to worry about field size?
I don't think so.
Isn't that inherently included in your?
Yeah, it's inherent in the inverse square. Okay, it's built into the inverse square calculation. Okay, so 139. So now we're going to do 139 times, what's our inverse square?
120 over 80.
Is it 120?
110. 110.
110 over 80 squared. Okay.
I dropped it when I took
Your calculator?
No, the ion trimmer. I dropped it.
Oh, okay.
Couple fingers.
Yeah, be careful. People get confused when you'll see this 100 and you'll see the 10, and then you'll do the inverse square and you'll put 100 in there just because you're looking at this 100, or you're looking at this 100, and you'll forget about this 10. Okay? So be careful. That's like one of the places most people make the mistake. It's 110 because you're 110 centimeters away. In this one, it's a little more obvious because you're in air. But sometimes when you have a situation like this where you have 100 and you have 10, people tend to put 100 there. Forget that extra 10. Okay, so what do we got?
We got 263.
Okay. So pretty close to our last problem, right? Okay. So both ways, TAR works, PDD works. Next. Okay, so now that's what we just did. You did 263. Example 4. Cobalt-60 beam delivers 100 R per minute at 80 centimeters from the source for a 10 by 16 field. Okay, so now it's not a square field anymore. We need to deliver 200 centigrade per day to a lung tumor treating with APPA fields. So this is a little bit more practical. The other two examples we did were more to get you guys a feeling of how to use these functions. And this is a little bit more applied. Okay, so 100 R per minute at 80 centimeters from the source in air for a 10 by 16 field. We need to deliver 200 centigrade per day to a lung tumor treating with APPA. Now we got two fields, not one. A field coming from here and a field coming from the back. Physician desires to give 100 centigrade per field. Okay, so 100 centigrade from this side and 100 centigrade from the other side. The fields are both 10 by 16. The AP depth is 12 centimeters, and the PA depth is 10 centimeters. Okay? And I'll draw that in a minute. I think it helps if you guys are doing assignments or tests. Just draw these out because you can visualize and see what's going on. The AP depth is 12, PA depth is 10. What are the treatment times for each beam? The patient is treated in SAD setups. And that's it. And I'm giving you FMED. Why do you think I need? Why do you think you need FMED? You thought you were done with FMED. Why do you think you need FMED?
Because you have exposure.
We have a Roentgen in the room.
Yeah, right.
Yep.
So you have to convert.
We have Roentgen, so we have to convert to centimeters. Correct. Okay. All right, so if we were, and then we're going to use this, I'll give you this equation. So when I say, what are the treatment times for each beam, here's the equation you're going to use for treatment time. So for Cobalt-60, we don't use monitor units. You folks are probably not going to use a Cobalt-60 beam, but in Cobalt-60, instead of typing in monitor units, they type in time, in minutes or seconds. So time is equal to dose per field, and we know that that's 100, so that's a known. That's 100. And then dose rate at Dmax times PDD. Okay, so we're going to use that. So we need to know dose rate at Dmax. What about PDD? Where are we going to get PDD?
The PDD will get from the table.
Okay. Is this 10x? No, Cobalt-60. Do you have a Cobalt-60 team? I think it's... You guys you each have a different book.
At least they're supposed to be similar, though.
Yeah,
I know.
different pitch.
You got it?
Yes, we do.
Okay.
This is PDD at 80 centimeter SSD,
Yep.
which is what we're at.
Okay. So, all right, so here's the patient. Here's the patient's body, and then one beam comes in like this, and then the other beam, AP is 12. So here's 12 from this side and 10 from this side. Okay, and the other beam comes in like this. Okay, and this depth is 10 and that depth is 12. That's basically a schematic of what's going on here. Okay, so we'll treat the PA first, and then we'll rotate the gantry around, and the isocenter is right here. Rotate the gantry around, and we'll treat the AP. What do you think? Which one do you think is going to require more time? The AP or PA to deliver the same dose? The AP is deeper, right? So it's going to require a little more time. Okay, fine. All right. So let's start. Let's do it beam by beam. Okay, so you can actually forget one beam and just work on one beam. All right, so first beam. Let's do the AP first.
All right, you need to get a smart field for
Okay? So field size, and they're going to be the same, right, in this case. Field size equals what? How do we go from rectangle to the square?
2AB over A plus B.
Yeah, 2AB. So what's 2 times what's A?
10 2B is 16 or vice versa.
Okay. Equals? And by the way, the answer is going to be between 10 and 16.
Yeah.
Okay.
12.3.
What is it?
12.3.
12.3, okay. 12.3, okay, so we have a field size, great.
So we go to our table, we have a 12.3 by 12.3. Do we just use the 12 by 12 or do we extrapolate from the table?
You could just use a 12 by 12.
Okay. Have a depth of 12.
Okay, so our depth is 12. We have a field size, we have a depth, and we have an exposure rate. Okay, first let's get rid of this R per minute. How about it? How do we get rid of that and make it centigrade per minute?
Just multiply by F med.
Yeah, that's it. Okay, so 100 times 0.95 or 0.95 equals 95. So we have 95 CGY per minute at 80 centimeters from the source. And are we treating SAD or SSD? Physicians, is that time? Yes, it's SSD setups. Okay, so our SSD setup. So our SSD is going to be, it's going to be 80, right? So we're going to use 80 as our SSD. Okay, so 95. Now, how do we go? So now we have a dose rate in air, but don't we need a dose rate in tissue? Because we're treating the patient and the patient's tissue, so we need a dose rate in tissue. So what do we need?
We need the TAR.
Yeah. Do you guys have the TAR table in there?
Yeah.
You do?
Yeah. For a 12 by 12 field at a depth of 12 centimeters, it's 0.630.
We're
Do we divide or multiply by time? This is in air. 95 is in air. So we need to go to the tissue.
Dose in air times TAR. That's dose in tissue.
Dose in air times TAR is dose in tissue. So we need dose in tissue. So TAR is dose in tissue divided by dose in air.
Does this FMAT already specify tissue?
No.
No.
FMAT just converts Roentgen to centigrade. But that's centigrade in air. Centigrade in air. Okay, so then what do we do? 95 times, I heard somebody say times TAR, right?
Yeah, times 0.630.
Times 0.630. What depth was that for? 12?
Yeah.
Okay, good. So this is TAR 1212. So what number do I get? 95 times 0.630. That's about 0.6.
I've got one here somewhere.
You got a calculator?
I'm gonna check.
I have one in here.
Yeah, I brought it.
Oh, good.
59.85.
59.8. Okay, so it's just 59.8. And that's units of?
Centigrade per minute.
Okay. Cool. All right, so now we have a dose rate in tissue at a depth of 12, but we have a problem. Oh, we can't do that. Why not? We can't do that because look at our setup. This is where drawing the triangles is important. Okay, so we have 80 centimeters here, and then we're at a depth of 12. What's our distance to our point of interest? 92. We didn't take that into account.
We didn't adjust the field size.
Yeah.
Okay.
Should we do it that way, or is there another way we could do this? So that's at, what distance from the source does that correspond to? We're in tissue now, but what distance to the source does that correspond to?
Trying to.
No, the one we just calculated.
Oh, the one we just calculated was for 8.
That's 8. Yeah, we haven't done any of the square. So we have it for 8. So okay, now we have the dose rate at Dmax now. So how do we get the dose at 12?
Okay, use a PDD.
Yeah, we can use PDD. Okay, so we're going to take that times or divided by PDD?
Times.
Times PDD? We want that number to go up or down. That number is not going to go lower as we get deeper.
Yeah.
It's going to go lower, right? So, and the definition of PDD is dose in tissue divided by dose
Dmax.
in Dmax. We have dose in Dmax, so rearranging that, we have dose Dmax times PDD equals dose in tissue. Okay, cool. So what's the PDD? Now we need a PDD of, the SSD is 80, that's good. The depth, we need a PDD of depth of 12, and we need a PDD for what field size?
12 by 12.
12 by 12, because it's the field size on the surface.
Surface, which is 49.5.
Times 0.495 equals PDD. And by the way, that's this PDD that we're doing over here. PDD of 12, 12. All right, cool. And so now that dose rate is what?
6.495.
Yeah, so it's 59.8 times 0.495.
29.6.
29.6. Okay, so time equals 100 divided by 29.6 CGY per minute. And what's that?
.38.
All right. So for the AP beam, the therapist is going to turn the cobalt-60 beam for 3.38 minutes. Now, for the same treatment, say this was happening 6 months from this time. Is it still going to be 3.38 minutes? Say the guy came back for the same treatment 6 months from now, same dose, same treatment, same everything, cobalt-60. Is it going to be the same time? Yeah.
As long as you didn't gain or lose weight.
Okay, so you vote for yes. Any other votes?
With the caveat.
Okay.
You mean, well, no, you wouldn't. You'd have to count for the decay of your
I have a question.
Mhm.
I think the FMED already took the tissue into consideration, because if it doesn't, the FMED should be 0.836 or 37. That's a conversion from Rankine to dosing the air, but it's 0.995.
You think that's too low or too high?
Too high.
I think it's too high.
Yeah,
Well,
for air. So it's around the tissue. It's around the muscle.
I think that's just an example.
Yeah.
Yeah. That 0.95, that may not be a true value. Yeah. See, the thing with the TAR, what FMED doesn't consider that TAR does, TAR considers all the scatter that's going on. FMED does not consider any scatter. Okay. And FMED doesn't know how deep it is. Okay, so TR considers the depth too. So FMED just converts Rankine to centigrade in air. You have to think about it that as in air. It doesn't know about scatter, it doesn't know about depth. Okay. Okay, so decay, yes. Who said decay? Cobalt-60. So then at 6 months from now, what is that going to be higher or lower?
If you haven't changed your source, the time's going to be increased.
Yeah, time's going to increase because you have a weaker source. Okay, let's keep going. So that's the answer. Did we get it right? Oh, here. So I did
Yeah.
AP, determine dose rate at 12 cm depth. Look up PDD for 80 centimeters, depth 12. Okay, and field size. And then what I did here is this is an interpolation. So you guys can look at this. This is how you interpolate between fields. Practice interpolation is very useful. Dose rate at 12 cm, depth is, so I gave you, what did I give you? I gave you an air. Yeah, I gave you an air. Wait, is this a second? This is one way of doing it. Look up TAR, dose rate at Dmax. Oh, no, that's dose rate at Dmax, right? And then this is how you get dose rate at depth, right? So that's what we did.
Your time is not as long as ours.
Yeah, you have a whole minute and a third less than us. We used,
Okay.
we have 0.17.
Did we get this right? Did we get this 99 right? Or was our chicken scratching there?
Our,
No, we didn't.
no, our,
Wait, that TAR looks a little. Oh, that TAR is really small. That's. Oh no. Oh, you know what? We did wrong.
what?
This. This is not. We should have used the TAR for Dmax. We should have used back scatter factor here, and then we could use the PDD. Okay. So okay, good. So we caught that. That's a good way of learning. So give me the TAR for Dmax.
The TAR for Dmax.
So when you look at this lecture, make sure you look at this part of it before we correct it. For field size is 12. Is it in there or no? TR Dmax, BSF.
Is there a separate table for DSM?
Did you find the TR table?
We were using Oncology Max.
Oh no, that's not it.
That's not it.
That's a different. We're going to do that next class.
Okay.
Mars. So we don't have a TR table?
I don't think we have.
I think you have one here.
Were you reading off of the TMR table?
Yeah.
Oh, you are? Yeah.
That's why we read off the wrong table.
You see how this can be confusing?
Yes. I was going to ask about that, but it's not that.
Did you find a TR table?
Yeah, it's 1 point here.
Okay, that's another thing. The TAR at Dmax is usually bigger than 1.
Yeah.
Okay, so what do you have?
1.046. 1.046.
Okay, 1.046. .046. Okay, so let's clean these. Let's clean this stuff up. Okay, what do I get now? So 95 times 1.046.
99.4.
99.4. Okay, good. That's looking a little bit better. Then now we can use the PDD. This PDD is correct. So times 0.0495, which is PDD for 12 and 12, and that's equal to what?
49.2.
49.2. And then what does that come out to?
So 100 divided by that?
Yeah.
2.03.
Aha. That sounds like what we got in the next slide. 2.03.
Yeah.
Okay. So we just made a boo-boo there with the depth of the TAR because we needed to calculate what the dose rate was in tissue at Dmax, not in tissue at 12. We could have done tissue at 12, but we just had to do our inverse square. We just had to calculate our inverse square correctly. Okay. So, and then the PA, same idea. PDD for 10. So now you're just using a PDD for 10 cm depth, then a dose rate at 10 cm. So you're just kind of reversing everything. The only difference there is that you've got a different PDD. Okay. So those are some examples. Comments on SSD setups. the treatment table had to be moved to ensure that we had 80 centimeters SSD for both beams. Okay? So think about this. For the first one, it was 80 SSD. The patient's on the table and they set up 80 SSD. Now that 80 SSD, that's the isocenter for a cobalt-60 beam. So if you rotate the cobalt-60 beam around, and what would be my SSD now? If I don't move anything except rotate the cobalt-60 beam around to the PA position, what's my SSD? You have enough information to tell me this.
What a PhD.
Well, let's draw a picture. So patient, there's 80 SSD, okay, for the first one. Okay, now this is my isocenter. That point is my isocenter.
Right.
I'm rotating around
If you
this.
use nothing else, your patient's 22 centimeters thick plus the table, so your SSD is 58.
Right, 58. So as I come around, my SSD at this point will be 58. Okay? We don't want an SSD at 58 because we don't have PDD tables for that. We want an SSD of 80. So what do?
Check the table.
Right, bring the table up 22 cm and then treat. Okay? So that's one of the disadvantages about SSD setups. You got to move the table. If we don't move the couch, the SSDs will not be 80. Therefore, we would have to adjust our PDDs with the Mayneord factor. Okay, so if we don't want to move the couch, we can say, well, we're going to put the isocenter in the middle and make this SSD, 88, and make the other SSD 90, and calculate what the PDDs are for an SSD of 88 and an SSD of 90. Okay, so you could do that, and you wouldn't have to move the table. But you've got two SSDs to play with and a lot more calculations. If the SSDs were not 80, the field size on the surface of the patient would be different from 12.3 requirements to determine new field size for each beam, and using these to look up factors in the PDD tables, right? So the field sizes will no longer be 12.3 like they are with a constant SSD, they'd be something else. SSD setups are seldom used except for single field treatments. So to say SSD setups are not used is incorrect, because if you have a single AP or a single PA, therapists may set up to 100 SSD just because it's really easy to set up to. You know, with an ODI, they just shine the ODI on the patient, bring the table up and down, hit 100, and it's very simple to set up to. Okay, same situation. Now we're going to do this in SAD setup. Same calculation in SAD. So we'll see. That way you guys get an idea of the differences in calculations. So an SAD setup, the isocenter of the machine is now placed. Here's our patient. So this is 12 and this is 10. We're going to put the isocenter here this time. We're not going to put it here and then here. We're just going to put it in one spot. We're going to put it right there. And we're going to treat AP, then rotate around and treat PA. Okay? No movement of patient. All right, so let's see, how are we going to do that? So patient's tumor is placed at the point that intersects the gantry-rotational isocenter and the columnar isocenter. The AP SSD will be 68 cm. Okay, and the PA SSD will be 7. That makes sense. The source to tumor distance will be 80 centimeters in AP as well as PA, right? Because the source to isocenter distance is constant for both beams. They're both 80. So let's determine the dose rate from the AP. We're going to use the same equation, time equals dose divided by dose rate times PDD. Actually, no, we don't. We're not going to use the PDD this time. We're just going to use. We're going to calculate the dose rate at our point of interest, and so we don't need PDD. It was back there somewhere, right here. So determine the dose rate at this point from the AP beam at a depth of 12. Okay, so dose rate in air was given 100 R per minute times 0.95 was F med, so the dose rate was 95 centigrade per minute in air at a distance of 80. Okay, then we're going to use the TAR. We're going to use this TAR. I did the whole solution for you. Okay, well we can go through it. Then we're going to use the TAR. Let's make sure these are right. Field size. Is that right?
Yes.
Okay. Well, we said the field size. If you think about it, though, the field size was 12.3 on the surface before, right?
Yeah.
And that covered the tumor. The tumor was in here somewhere. Okay. And that was the field size that was determined that was going to cover the tumor at a depth, at a deeper depth. Okay, so now, in reality, I mean, this is a simplified version, but in reality, your TAR is at your point of interest, and if the field size at 12.3 covered the tumor, you should be using a different field size, because your TAR is for the field size at your point of interest. What is your field size at that point? If 12.3 was at the surface originally,
Even though you're bringing the patient, the tumor up to ISO center, if nothing else has changed, would you, like, okay, so
Because
you have your
distance
12.3 by
difference,
12.3.
It's 80.
okay.
It's 80.
So are you saying that the field size is okay?
Yeah.
Mathematically, for this problem, yes, the field size is fine, but physically, would you, so your 12.3 spreads out from inverse square. If you bring the patient...
Not inverse square.
or
Similar triangles.
Similar triangles, right. If you bring your patient up...
Whatever it is.
Right, if you bring your patient up to isocenter, then you wouldn't have to change anything, would you?
Well, in the
Or-
previous problem, the 12.3 was at the surface, but the field size of the patient's tumor was bigger than 12.3. So you needed a field size that's bigger at the tumor, bigger than 12.3. 12.3 on the surface just satisfied that.
Okay.
Okay, so the field size at the tumor needs to be a little bit bigger to be able to cover that.
Yeah, but in this problem, they're saying because in the previous problem, the SSD is 80, but now you put the tumor at the 80, you get our SAD setup. The distance doesn't change.
Right.
So we got the same field size.
Okay, so in the previous problem,
Yeah, SSD is,
here's your patient and here's your tumor.
yeah.
Okay, the field size was 12.3 on the surface.
Yeah.
What was the field size on the patient?
It will be bigger.
What is it? Tell me what it is.
We draw my similar triangles. If 80 over 12.3 equals... the depth was 12?
Yeah.
Correct. 12.3 times 92 over 8.
Yep. So what is it?
Josh, can you correct the difference?
14.1.
14.1. So at the depth of the tumor, you need a field size of 14.1 cm to cover it. There's nothing you can do about that. That's how big the tumor is, no matter where you put the patient. Okay, so if we now put the patient at the isocenter, we still need a field size here of 14.1. Because that's the size of the tumor. Okay. You get that? Okay, so that's just something to think about. Now, I simplified it here so we didn't have to do that step. I just assumed we're going to assume the tumor got small. Okay.
Hey, it's already received treatment.
It's already received some treatment, and it shrunk a little bit, and we're going to use a field size of 12.3 more. But it's just something to keep in mind. It's just like a mental exercise that we just did. Okay. So use TAR. We're going to use this TAR to cover our tumor. We're going to assume that we're going to cover it with a field size of 12.3. And what about the depth? Is that okay? Our point of interest is at a depth of 12, so that's okay. All right. Now, what about the starting point, 80 cm? Remember, when we're using TAR, we want to make sure that their point of interest is the same distance to the source in air and in tumor. Is that okay? We've got 80 cm, a dose rate at 80 cm in air. Is this 80 cm?
Yeah.
Yes, okay, so that's okay. So we can use this TAR. So we're going to start with this dose rate. Do we multiply or divide by this TAR?
Multiply.
Multiply? Yeah, usually when you go to air to tissue, you multiply it. When you go to tissue to air, you multiply. Okay. So the TAR from tables is 0.66. Okay, so then the dose rate at a depth of 12 cm at a distance of 80 centimeters from the source is 95 times 0.66. So there's our dose rate at our point of interest. And then time to deliver 100 centigrade is 100 divided by 62.7, 1.5 minutes. See that that was what, one step. See how easy that was? That was one step because we're given the dose rate at isocenter, and we're treating at isocenter. So there's no inverse square issue to take care of. Okay. And look at how much shorter. Why is it so much shorter? It's not 2.03 anymore. It's 1.59. Why is it so much
Just
shorter?
get close.
You're a lot closer. Perfect. And then PA dose rate, same idea. 95 times the TAR. The only thing that changes is the depth. You get a higher dose rate and shorter time. Okay. Comments about SAD setups. No need to move the couch. We didn't have to move the couch. The only thing that changed, let's see, field size, possibly field size. In this case, we didn't have to change our field size, and depth. Depth definitely had to change. The tumor is placed at the machine isocenter. We used TAR tables, and Jimmy, you found some TAR tables in there, right?
Yeah.
Okay. Most treatments, but they're none in com. Is that right?
At least not in the appendix.
It's not in the appendix, so they're none in com, but Johnson Cunningham has them. Did you guys get Johnson Cunningham yet?
Yeah.
Okay. Oh, you need it for this course, for Dr. Hahn's course. Most treatments today are SAD setups. Linux use monitor units instead of minutes. Okay. Rotation therapy. What about rotation therapy? Now, rotation therapy is the kind of therapy that's delivered while the machine rotates during delivery. Okay, so you'll start at a certain gantry position, you'll turn on the beam, and the gantry will move, rotate through, and then stop at some gantry position. Typically, write this stuff. This is supposed to keep going. Okay, typically, this isn't used as much anymore, but back in the days, even before 3D conformal radiation therapy, we would use the rotation therapy for prostates because the prostate's nicely in the center of the body. It's a round structure, and the isodose distribution for rotational therapy, it kind of follows the external surface, so it would look something like this. It would look oval. It would sort of follow this. So it's a nice circular distribution for the prostate, and you can deliver quickly. And there's only one monitor unit you have to type in. You just type in one set of monitor units, and you turn the beam on, and away you go. Instead of delivering it from many beam angles. Okay, so it simplifies the treatment too. But how do you calculate monitor units for rotational therapy? You don't have one depth anymore. You've got lots of depths. Okay. You have one. You can probably set one field size. It would be a little complicated if you had to change field sizes as you went. So you have one field size, and you have many depths. So what we would do is very simply take an average of the depths. This is just a simple simplification of it. We would take the average of the depths and look up the TAR. Okay, so we would, even before CT scanning and before we had 3D conformal therapy, we had, the way we would get the outline of the patient's surface, and I think I might have mentioned this before, we take solder wire. We take a big long piece of solder wire this long, and as the patient was lying down on the simulator, we would wrap the solder wire on the patient. And the solder wires, we used to take solder. And then we would lift the solder wire, trying not to change the shape of it, and we'd place it on a piece of tracing paper. And we would trace the patient's external surface. And we just have, this is 2D. We just have one sheet. And the doctor would draw the prostate on that sheet of paper. And from there, we could calculate the average depth from there. Just take measurements and calculate the average depth, and then use that D to look up the TAR. And the field size, the field size would just be set. The doctor would look at this and say, well, I need this much from this direction, this much from this direction, and he would give himself a little bit of a margin and just pick one field size. That would cover it all the way around. So that's rotation therapy. Okay, let's go into SAR, scatter error ratio. So we talked about TAR. Now, let's introduce SAR. SAR is simply your TAR that we were just using minus this TAR. Remember that one? That's the zero field TAR for the same depth. So in SAR, what we're doing is we're taking all the dose that comes from the TAR, and we're taking out the primary component. And so what we're left with is just scatter component. Okay. So this gives us information about how much scatters in the beam. Okay. And so the dose from scattered radiation is proportional to this. So so let's see. Let me tell you what all these. I wonder if there's another slide that shows this better. No. Okay. Let's do this. So let's take an example. This is so So we're going to use a round field size. This is a beam's eye view. The beam's coming this way into the board, and there's our central axis. Okay, and there's a patient over there. We're treating a patient with a circular field. Okay, and we want to know what the dose from scatter is at the central axis, at the center of this beam. Okay, and we could do that by using this formula. So the delta theta is, we're going to go around like this. And we're going to measure ray lines to each of these, to the edge of the field. This is a circular field, so we're measuring ray lines to this edge of the field. Delta theta is here. It is one of those, the size of that piece. How we decide to divide it. Delta theta can be 10 degrees, could be 5, could be 30, could be anything. Okay? Whatever we decide it to be. Divided by 2 pi. Okay? So this is, what this is the ratio of the entire circle. It's one part of it. Okay? So we're looking at one piece of this. Times the scatter component of each of those ray lines for ray lines going from 1 to n. Okay? And this could be I equals 1, and then this is 2, 3, 4, 5, all the way to n for all the ray lines. So the total, all this means is that the dose from scatter is the total scatter component as you look at the scatter from every ray line. And why do we have to look at every ray line? If it's a circle, it's the same for each one, so it's simple. But we don't always treat the circles. A lot of our fields look like this, or look like that. They're different shapes, right? So if we take the central axis of the beam and we look at the ray lines, they're going to be different. And the scatter component is going to be different as they go around. Okay, that's still my little delta theta. But the scatter component is going to be different on this ray line than it is in this ray line. Okay?
So for that situation,
Yeah.
you have that wing on the top right.
Mm-hmm.
If you extend the ray line through the block,
Mm-hmm.
you would bisect that wing. Would you count the area above the extended ray for?
You know this one right here?
Yeah.
Yeah, this has to be considered as well.
But would you include that with each individual theta that would pass it, or do you include that in the one where it's a continuous field?
Well, the way you treat something like this is you'd have a ray line, and let's exaggerate it, let's say it goes like that. So you'd have a ray line that goes all the way out here, and so you'd use the full ray line, but you would subtract what's under the block.
Okay.
So that would be a subtraction.
All right.
So you're assuming the scatter is coming from here. You're getting all the scatter from here. Actually, you're getting all the scatter from here to here. But it's not true because part of this is being blocked. So you're just subtracting that ray that goes to the edge of the block. Okay. So that's how you handle that. And this is the algorithm that was used for many years. This is called it's on the next slide. It's called, and this is to calculate dose, the Clarkson algorithm, because all the examples we did today were square field sizes that are very well behaved, and they can be described by the data that's in these tables, and it's easy for us to calculate the dose. Once you start having field sizes that look like this, the scatter now, you can't get an equivalent square from that. Okay, and even if you have field sizes that are more regular, that's your field size, and the doctor decides to draw blocks that may look like this, with the MLCs, brings MLCs in, and then draws another block like that. Even that's irregular. Okay, so we had to, at the time, back in the day, they had to figure out a way of calculating the dose for those irregular fields. That's where this comes in. Okay, and that's where the Clarkson algorithm, Clarkson's method, calculating dose from irregular fields. So the Clarkson algorithm takes into account that we've got irregular fields, and it calculates ray lines out to many points around the irregular fields, and it adds up all the scatter. And then it adds the primary dose to that, and that's the total dose. So use of blocks for MLC changes the shape of a field, which decreases scatter within a patient. Okay, so the scatter is going to go down. Dose rate is calculated by summing up the scatter component over 360 degrees around the point of interest. Around the point of interest. Ray lines are drawn every delta theta degrees at a distance of the line to the edge of the block or the edge of the field, and that ray line is used as the radius for the SAR calculation. or SAR look like. The average SAR is then used to calculate the average TAR using the equation in the previous slide, using that previous equation. So that's it. So then you add up you add all this up, okay, and that's your SAR. Okay, and then you can calculate your TAR by bringing this over to the other side. You add the primary component to get your TAR. Okay. When I learned this when I was doing my master's degree, we actually had to do a problem in class. It took us like an hour to do it. The teacher would put down a field size that kind of looked like this. He said, "Okay, guys, start measuring all these rays and tell me." And he would give us. And actually, you know what? Open John's Equation because I think there's either the SARs in there or. But if you know the TAR, you know the SAR because you can subtract the primary component. There it is, scatter error ratios for circular fields. Okay, so the top, along the top, you've got your radius, each of those R's. Okay, so you look up your R, and then scatter is depth of thing. So then you look at the depth that where your point of interest is at, and that's where you get your SAR. And so you need one of these per ray line. Add them all up, okay? And there's actually a calculation in John Cunningham where they go through the whole thing. And the calculation includes subtracting one of these. Okay? So that's SAR. So anyway, today's class is an introduction to dose functions. We covered the ones that were used in the past, but they're pretty simple, and I think you guys have a good idea of how to use. Next class, we're going to cover the dose functions that we use more commonly in the clinic, like TMRs. Yeah, TMRs mostly, TPRs. Okay? All right, cool. Okay.